everyone, my name is Dr. KCH Apparao, working as an associate professor in mechanical engineering department. Okay. So, in previous class, we derived the rate of heat transfer formulas Q12 in between the two plates. The conditions, the plates, if the both the plates are very long and parallel plates, we saw that condition. If the one surface is enclosed with another surface, we derived the rate of heat transfer between those plates also. Next to if the two plates, one shield is placed between the two plates, then the rate of heat transfer between those condition also we already derived. Now we'll see some numericals based upon those formulas which are discussed in previous class. These are the numericals already given in the question bank. We can cover those numericals. Okay, the first numerical, the condition: two parallel infinite gray surfaces. So parallel infinite gray surfaces. That means areas of both surfaces are same. A1, A2 is equal to A. Parallel infinite means we can't measure the areas, so we can take areas of both plates or say gray surfaces. So are maintained at a temperature. So gray surface means we can consider the emissivities. If the surfaces are black surfaces, then emissivities are 1. If the gray surfaces emissivities are less than 1, then you have to consider the emissivities of both the plates. Okay. These plates are maintained at a temperature. So first plate temperature is equal to 400 Kelvin. Second plate temperature is equal to 500 Kelvin. Okay. The temperature of the hot surface is increased to 600. Again, this is the first condition. Next to this second surface temperature, so has been increased from T2 to T2 dash. It means 500 to 600. Okay. So in this case, we have to find out the rate of heat transfer Q12. So when the temperature is increased, in that condition also, we have to find out the rate of heat transfer. That is Q12 dash. By what factor is the net radiation exchange per unit area? Area is equal to unit. Okay. So we have to find out the percentage. Assume emissivity of colder and hotter surface. So emissivities of the first surface 0. The first one is the colder, means this is the epsilon 2 is equal to 0.9. Epsilon 1 is equal to 0.7. Okay. So these are the given data. Emissivity is given. Area, unit area. So you can take A is equal to 1. Temperatures has been given. Then the surface temperature of the second body has been increased. So that condition. So here two conditions. One is initial temperatures, temperature of first body, temperature of the second body. So next to increased rate of heat transfer at increased temperature. So first we will see. So these are the two surfaces. Temperature of first one. So this one is the temperature T1 is equal to 400 Kelvin. Okay. So next to T2 is equal to, take heat transfer takes place from Q2 to okay. T2 is equal to 500 Kelvin. Okay. So next emissivities, this is E2 is equal to colder and the hotter surfaces. This is the colder, epsilon 1 is equal to 0.9. Epsilon 2 is equal to 0.7. Okay. So areas EA and EA. Then you know this formula for this one, we already derived in previous class. Heat transfer takes place from 2 to 1. Okay, because due to temperature of the second body is higher than the first body. Q2 to 2 is 2 to 1 is equal to same formula. Uh, so Q by A you can take unit to per unit increase. Okay. Otherwise, A is equal to 1. You can take sigma T2 to the power of 4 minus T1 to the power of 4 divided by 1 by epsilon 2 plus epsilon 1 minus 1. Okay. So by using this formula, you can find out. So this is the 5.67 into T2 is the 500 by 100 to the power of 4 minus 400 by 100 to the power of 4. So because 10 to the power of minus 8, just I am writing like this one. Okay. By epsilon 2 1 by 0.7 plus 1 by 0.9 minus 1. So okay, if you solve this one, you will get to this answer. So Q12 is equal to sigma into T1 to the power of 4 minus T2 to the power of 4. Just here T1, this is you are taking T1 here, or T2 to the power of 4 minus T1 to the power of 4, epsilon 2 and epsilon 1. Okay. So sigma is nothing but 5.67 into 10 to the power of minus 8 into, so T2 is 35 to 500 to the power of 4 minus 400 to the power of, okay, 1 by epsilon 0.7 plus 1 by 0.9 minus 1. So this is the value Q by Q12. So Q21, otherwise Q21 or Q12. Just Q21 means you can reverse this one, hot body here, cold body here. Okay. So that is the value is equal to 1359 watt per meter square. So this is the value Q by A. Okay. Next to the temperature has been increases T2 to T2 dash, that is 500 to 600. The temperature of the hot body has been increased. Okay. So at that condition, it means so we'll take same formula. You can use this one. Second condition Q12 dash or Q21 dash, anything. So hot to cold. So sigma into T1 to the power of 4. So here T2 is equal to nothing but it was increased, 5 to 600, 500 to 600, next 600 to the power of 4 minus 400 to the power of 4. By area you can write like this one. So by 1 by 0.7 plus 0.1 is equal to minus 1. So this value is equal to 3830. Now we'll see the percentage of this one. Q12 dash minus Q12 by Q12 is equal to, so the increased value is equal to 18%. Okay. So in this way, just you can solve the numericals. You will see one more numerical. Two very large parallel plates. Okay. Very large means we can take areas of both the plates are set. So two very large parallel plates, emissivity is equal to 0.3 and epsilon 2 is equal to 0.8. Okay. Determine the percentage reduction in radiation to energy transfer when the polished aluminum shield. Here shield is placed in between the two plates. That is the epsilon 3 is equal to 0.04. So this one is placed. Okay. So you will see this condition. First we will find out the without shield and with shield. So then the percentage of reduction in the heat transfer will find out. So first we will find out the rate of heat transfer between 1 to 2 without shield. You know the formula sigma A into T1 to the power of 4 minus T2 to the power of 4 by 1 by epsilon 1 plus epsilon 2 minus 1. So by using this formula, you can find out the Q12. So Q12 already solved this one. Here we can see Q12 is equal to like this one. Okay. So Q12 is equal to sigma into T1 to the power of 4 minus T2 to the power of 4 by 1 by epsilon 1 plus and epsilon 2. So this is the value. So here the temperatures of both the plates are not given. Just to, you can keep like this one. So this is the value into, so 0.279 into sigma T1 to the power of 4 minus T2 to the power of 4. Now by intersecting or by placing the shield with shield. So this is the condition with shield. So then the formula will be like this one. So sigma T1 to the power of 4 minus T to the power of 4 initial temperature minus final temperature by resistances. 1 by epsilon 1 plus 1 by epsilon 3 minus 1, 1 by epsilon 3 plus 1 by epsilon 2 minus 1. So you know that epsilon values, epsilon 1, 2, 3, you know that. If you substitute the values, you will get this one. Okay. Then the percentage of heat transfer reduction. So that is the Q1 is more. By placing the shield, automatically heat transfer rate will be decreased. Then so Q1 minus Q2 by Q1 into 100. So that is 93% has been decreased due to the effect of this shield. Okay. So we'll see one more numerical. Calculate the net radiant heat exchange per meter square area for two large parallel plates. So here also large parallel plates means areas A1 is equal to A2 is equal to A. Temperatures also given 427 convert into 273 kelvins. Next to this is T1. Similarly T2 is equal to 27 plus 273. Okay, 3300 kelvin. So this one is 700 kelvin. Okay, so these are the temperatures. Emissivity of the hot body also given. Epsilon 1 is equal to 0.9. Emissivity of the cold body, epsilon 2 is equal to 0.6. Here also, if a polished aluminum shield is placed between them, find the percentage reduction. Similar numerical. So epsilon 3 also given 0.4. So first of all, we have to find out the rate of heat transfer between the two plates without shield, Q12. Next to rate of heat transfer between the two plates with shield. First we will see without shield condition. So you know that formula. The formula is equal to sigma T1 to the power of 4 minus T to the power of 4 into area by 1 by epsilon 1 plus epsilon 2 minus 1. If you substitute the values sigma 5.67 into 700 by 100, because 10 to the power of minus 8, you can write like this one. Okay. So plus minus 300 by 100 to the power of 4 by epsilon 1 and epsilon 2. The value is equal to like this one. Okay. So this is the value. Next condition with shield. With shield Q13 is equal to Q32. You know this one. It means you can equal this one. A1 sigma T1 to the power of 4 minus T3 to the power of 4. So 1 by epsilon 1 plus 1 by epsilon 3 minus 1. So the rate of heat transfer into the shield and from the shield same. So here also same formula. If you solve this one automatically, okay, then we can find out the temperature of the shield. Temperature of the shield. So this is the equation X. So X, by using this formula, you can find out the temperature of the shield. If you know the temperature of the shield, then you can use that Q12 net. Q12 net is equal to sigma T1 to the power 4 minus T3 to the power 4 by 1 by epsilon 1 plus 1 by epsilon 3 minus 1. Okay. So this is the value. Okay. Reduction in heat flow due to shield is equal to Q12 minus Q13. Okay. So this is the value. Then percentage, you can find out the percentage. The percentage of reduction is equal to 96.5%. Okay. So this is the one more numerical. Two large plates are maintained at a temperature. So T1 900 Kelvin, T2 500 Kelvin. Okay. So each plate has area. Area is also given 6 square. So compare the net heat exchange between the plates. First, both the plates are black. Black means emissivity are same. Epsilon 1, epsilon 2 is equal to 1. So plates have emissivity. So epsilon 1 and epsilon 2 is equal to 0.5. This is the condition. This is the another condition. The first condition Q12. The formula is equal to sigma A T1 to the power 4 minus T to the power 4 by 1 by epsilon 1 plus 1 by epsilon 2 minus 1. This is the formula. If you substitute the values, because you know all the values, area, uh, you know that is area is equal to 6 meters square. Okay, sigma 5.67 into T1 to the power of 4, you know that 900 by 100 to the power of 4. So this is the value. Q1 to net is equal to 201.9 into 10 to the power of minus 3. So this is the condition when if you consider the emissivities, because the plates are gray. So these are the plates are black bodies, black surfaces are black plates. These are the gray surfaces. Epsilon 1 is equal to epsilon 2 is equal to 0.5. So same formula you can use, and if you substitute the values, you will get the answer. So then you can compare the both of those. So emissivity between the black bodies, the rate of heat transfer between the black bodies are very high compared to gray bodies. So this is the one more numerical just to determine the radiant heat exchange between the two plates. Emissivities of first plate given, second plate also given, temperatures also given. Okay. So if a thin copper plate is so here also shield is placed. Epsilon 3 is equal to 0.1. Epsilon 3. Okay. So then first of all Q1 to net. Okay. You know that formula QA T1 to the power of 4 minus T2 to the power of 4. So with considering the shield also 1 by epsilon 1 plus 1 by epsilon 3 minus 1 plus 1 by epsilon 3 plus 1 by epsilon 2 minus 1. Okay. So with shield, so this is the Q net. If you substitute all the values, because epsilon 1 0.8, epsilon 3 0.1, epsilon 3 0.1, epsilon 2 0.5. If you substitute all the values, then we'll get the rate of heat transfer between the two plates with the shield, with the effect of the shield. Okay, this is the rate of heat transfer. So this is the one more numerical. Just I'm leaving this one. Just you can solve this one. Okay, these are the different textbooks. You can refer to solve the numericals which are based upon the plates, gray surfaces. Okay. So thank you listening this class. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.